All right, welcome. Today we're going to dive into one of the most powerful tools you have in your calculus toolkit, substitution, specifically for definite integrals. Look, if you've ever just stared at a really messy integral and felt completely stuck, well, you are in exactly the right place. Let's get right into it.
You know, this quote just nails the whole idea of what we're about to do. We're not just swapping out one letter for another. No, we are fundamentally changing our perspective. It's like we're teleporting a problem from a really complex world into a much, much simpler one.
So think of it this way. Some integrals, when you see them in their original x world, are just a total mess. They're tangled, they're complicated, and trying to solve them directly is a huge headache. But what if you had a way to just, poof, teleport them to a brand new place where the solution is suddenly obvious? Well, that's exactly what substitution lets us do.
And this right here shows that transformation perfectly. On the left, you've got the x world. And yeah, that integral looks pretty intimidating, right? You've got a function inside another function, it's multiplied by a derivative. But then, with the right substitution, it just collapses into that beautifully simple form you see on the right. That's the u world. It really shows you just how elegant this method can be.
And here's the best part. This is the crucial point for definite integrals. Unlike the indefinite ones, you don't ever have to substitute back at the end. We make the journey to the u world, we find our answer there, and that's it. We're done. It is so much cleaner, it's faster, and trust me, it helps you avoid a ton of common mistakes.
Okay, so how do we actually make this journey? Well, it all comes down to 4 simple steps, but with one golden rule you absolutely cannot forget. When you change the variable, you must also change your bounds of integration. Say it with me. Change the variable, change the bounds. These are pretty much the keys to the kingdom. Step 1. You choose your u. It's usually that inner function. Step 2, you calculate its derivative, du. Step 3, and listen up, because this is the step where most people slip up, you convert your x bounds into u bounds. This is so critical. And finally, step 4, you just rewrite the whole integral in the u world and solve it. Easy.
All right, enough theory. Let's actually apply these steps. We're going to start with a classic polynomial integral. It looks kind of messy at first glance, but you'll see it's the perfect candidate for this method. So here's our problem. We need to find the definite integral of 2x times the quantity x squared plus 1 all cubed, going from x equals 0 to x equals 1. Now, could you try to expand that cubic term? Sure, but it would be a total nightmare. So let's change worlds instead.
Okay, let's follow our steps. For step 1, we'll choose that inner function. So let's make u equal to x squared plus 1. Simple enough. For step 2, we take the derivative. And look at that. Du is 2x dx, which is conveniently just sitting right there in our integral. Perfect. Now for step 3, the super important part, we plug our original x bounds into our u equation. So when x is 0, u is 1. When x is 1, u is 2. Bam! Our new world has totally new boundaries. And just like that, look what we have now. Our really complicated problem has transformed into the simple integral of u cubed from 1 to 2. I mean, come on, this is something we can solve in our sleep, right? The transformation is complete and it is beautiful.
So we just integrate u cubed to get u to the 4th over 4, we evaluate it from 2 down to 1, and we get our clean final answer, 15 over 4. Done. No back substituting, no mess, no fuss.
But hey, this method isn't just for polynomials. Oh no. Think of it like a universal passport. It works for trigonometry, for logarithms, for so much more. Let's level up and check out another example.
Okay, here we've got a trig integral. At first glance, it might look a little tricky, but it has the perfect structure for substitution. Take a look. Can you already spot what our u should be?
If you guessed u equals cosine of x, you are right on the money. Its derivative is negative sine of x dx, which is almost what we have. Now check out the bounds. This is cool. The lower x bound of 0 becomes a u bound of 1, and the upper x bound of pi over 2 becomes a u bound of 0. Whoa! The bounds actually flipped.
So now our new integral goes from 1 to 0, which feels a bit weird, right? But we can use this really neat property of integrals. If you flip the bounds of integration, you just flip the sign. So the integral from 1 to 0 of negative u squared is the exact same thing as the integral from 0 to 1 of positive u squared. And solving that gives us a super simple answer, 1/3.
Okay, let's do one last example to really drive this home. This time, a logarithmic integral. This one looks a little different, but you guessed it. It is tailor-made for our technique.
So here, the natural choice is obviously u equals the natural log of x. Why? Because its derivative is 1 over x dx, which we see perfectly right there in the problem. So we convert our bounds. When x is 1, u is 0. When x is e, u is 1. And once again, we have a brand new set of boundaries for our new world.
And just like that, our logarithmic beast transforms into literally one of the simplest integrals you can imagine, just the integral of u from 0 to 1. The solution is immediately obvious. It's 1/2, 0.5, done.
So, we've journeyed through polynomials, trig functions, and logs. What's the final takeaway here? What are the real keys to mastering this whole thing?
Okay, first and foremost, I'm going to say it again. Always change your bounds. It is the golden rule, it's the most common mistake, and if you can avoid it, you're halfway there. Second, you have to embrace the simplicity of the U-world. Once you're there, just stay there. Never go back. Remember, this whole method is a transformation tool. Its entire purpose is to make your life easier by turning these really complex problems into simple ones, and it works for all sorts of functions.
So, I'll leave you with this thought. You now have a technique that's really less about just crunching numbers and more about changing your whole perspective. It's like a key that unlocks simpler versions of really complex problems. So the only question left is, now that you can change worlds, what problems are you going to solve?